This lesson is for Advanced Algebra, Lesson 9-7 on logs with bases other than 10. The last time I talked to students in a video about logs, it was from Lesson 9-5, and we were doing common logs. Common logs have a base of 10. Keep in mind that for a common log, a lot of times the base is not even given. Today we're going to look at when you're doing a log problem and the base is given, it'll be a number other than 10. We're still going to set up the log problem in exponential form because all logs and all exponent problems have three parts. They both have a base. In the log form, it'll be a subscript number. In exponential form, it'll be the base of the exponent. The exponent is there. When it's in log form, the exponent will be the answer, or the piece of the information after the equal sign. And then there's always going to be a result. And when you do that in log form, it'll just be the log of a number. So you have a number, you have an exponent, and you have a base. And all those three pieces are the same when you deal with an exponential formed equation. There's three different types of problems that I'm going to look at with students. The first type are problems A and B. When you're given a log with a base other than 10 of a number, I would recommend that you fill in the fact that the answer is missing. So I fill it in with a question mark, but you can fill it in with a variable if you wish. Now rewrite it in exponential form. 9 is your base. We don't know what the power is yet, but we're trying to get to the number 81. So now you have to simply say 9 to the what is 81. Be careful here, a common wrong mistake for students to say, or wrong answer, is for students to say 9 times 9 and say that 9 is the answer. 9 times 9 is indeed 81, but 9 times 9 is not in exponent form. 9 times 9 means 9 times itself twice, and so the exponent there should be a 2. We know that 9 squared is 81, not 9 times 9. 9 times 9 is 81, but that's not an exponent. Let's try it again with a different question, like question B, log base 2 of 32. We don't know the power, but we know the base is a 2, and we're trying to get to 32. If students don't have the powers of 2 memorized, then they would just need to do some trial and error to determine the answer. 2 to the third is 8, so 8 times 2 is 16, 16 times 2 is 32. So that took us 5 base 2's to get there. So 2 to the fifth power is going to be 32. So the missing exponent is 5. And we had to do a little trial and error to get that answer. The next type of problem that I want to look at with students is when there's a radical involved. Log base 7 of the square root of 7. We don't know the answer, so I'm going to fill that in with a question mark. When I rewrite it in exponential form, I get base 7 raised to the unknown power equals square root of 7. Now this is the spot where students typically get stuck because it's very difficult to figure out what power you need. And the reason why we learned radicals in a previous chapter is because hopefully students remember that when you raise to a power or take the root, that there's an exponent that matches with that. Taking the square root of 7 is the same as taking 7 to the 1/2 power. Square roots and raising to the 1/2 are the same as each other. So there we have the exponent now. The exponent we're looking for is indeed that 1/2. Let's just do a couple for instances right now. What if this were a cube root? Then our exponent would have been a third. If this was a fifth root, our exponent would have been a 1/5. If this was a 10th root, our exponent would have been 1/10. So whenever you have a radical, convert that radical into fraction form and you'll have your answer. Into exponent fraction form. Sometimes they throw in weird ones like question D, where you've got a root and a power that you have to deal with. So again, let's rewrite it in exponential form. 12 to the what is the fourth root of 12 to the fifth. Hopefully students remember from one of our previous chapters on roots and powers. You can rewrite that as, since 4 is the root, that's going to go on the bottom of the fraction, and 5 is going to go on the top. So it's just like saying 12 to the 5/4 power. So just like on the previous one, the fraction exponent is what we're looking for, 5/4. We do not need a reciprocal power here because we're not solving. We're simply rewriting the radical in exponential form. So that is logs with roots. Next I want to look at logs with fractions. So we're going to look at E and F. Again, we're going to rewrite it in exponential form. 9 to the what is 1/9. The only way to get that base to flip over is if we have a negative exponent. That's something that students are simply going to need to memorize. The 9 stays as a 9, so the exponent there is simply going to be a 1. Similarly then, for question F, if I fill in the missing exponent with a question mark and rewrite it in exponential form, 7 to the what is 1/343. Because the number has now moved to the bottom of the fraction, I know that it needs to be negative, and then I'm going to do a little trial and error to figure out what power I need. I know it's going to be higher than 2 because 7 squared is 49. So I would double check on my calculator that 49 times 7 equals 343, and it does. So that means it took me 3 powers of 7 to get there. The next type of problem I'd like to look at is when all 3 parts are already filled in. We have a base, and this time we have an exponent that is given to us, but we don't know where we're headed. We don't know what we're taking the log of. So I'm going to rewrite this in exponential form, but I don't need to fill in what's missing. I have my 3 parts. So we have to remember which one of these is the exponent. Remember, the answer in a log problem is the exponent. So in this case, the exponent is the 3. So in all the other problems that we've done today, the thing that was missing was on the other side of the equal sign. Here, the number on the other side of the equal sign is given. It's the number in front of the log that we don't know. So we're simply going to rewrite it in exponential form. 5 to the 3 equals what we're looking for, x. So we just simply calculate. 5 to the 3 is 125, and we're finished. Common mistake there is for kids to believe that they're trying to rewrite this as 5 to the x equals 3, and then they get stuck because there's no way for them to figure that out. So know that when the exponent is given, you just simply calculate. Similarly, for our next example, example H, this time the base is the unknown element. So we're going to say x to the 1/2 is 4. So now students need to think very carefully. We're taking a number and square rooting it, and the result, the answer, is 4. Now if you know what that is, watch what we can do next if we didn't know what it was. If you don't know how to solve that, know that you can use your algebra skills to get x isolated. If we raise to the 2 on both sides, we'll be able to get x alone. The 1/2 and the 2 will cancel, and I end up with 4 squared, which is 16. And that number makes sense. If we took the square root of 16, wouldn't we get 4? So 16 is the base number that we're looking for. The last type of problem that students need to be comfortable doing of logs with other bases is when they ask you to rewrite it in another form. So if they give you an exponential problem and they say rewrite it, they might say rewrite it in another form, or they might say rewrite it in logarithmic form. Either way, you're going to write it the same way. Start with the word log, grab the base, which in this case is a 2, and then just be careful about where you put the other items. Here we have an exponent of x, so that needs to be the answer to the log problem, because the exponent is always the answer in a log. So that means we're taking the log base 2 of y equaling x. So that's the other type of problem that students need to be comfortable with, is rewriting it in another format. The last thing we're going to cover in the video is related to graphing. We're going to start by going over how to graph by hand an exponential equation, 2 to the x. So we're just going to fill in values for x here and then graph what it looks like. Before we get started, let's review the fact that this should be exponential growth. The b value, which is the number that's being raised to the power, is a number greater than 1. So I should be experiencing or seeing exponential growth here. Let's start with 2 for x. 2 squared is 4. 2 to the 1 is 2. 2 to the 0, be careful, is not 0, it's 1. And the reason is, as you go down the table this way, each time you're dividing by 2. So when we do 4 divided by 2, we get 2. 2 divided by 2, we get 1, not 0. Now 2 to the negative 1 is our next one. Remember that that means take the base and flip it over. So we just get 1/2. And then our last one is 2 to the negative 2, which again means we have to flip it over, but then it's going to be 2 squared on the bottom, which is 1/4. So now I'm going to go ahead and graph that. So here's my coordinates that I've graphed, and now when I connect them, it's going to look like an exponential curve. Be careful when you graph on the left here that it doesn't cross the x-axis, because remember the x-axis is an asymptote of the graph. Now when we want to graph the inverse of that, we simply switch x and y around. So if I take x equals 2 to the y, let's solve now for y, or let's rewrite it in logarithmic form. So I've got log base 2, the y is the exponent, and I'm trying to get to x. Now remember, when we're doing an inverse, the x and the y switch. So all I need to do here is rewrite my table and put the x's in the y spot and the y's in the x spot. So my y's are going to be -2, 0, 1, and 2, and my x's are going to be 1/4, 1/2, 1, 2, and 4. So now I'm going to graph those. And you'll see that from this graph, when we connect those coordinates, we get a very similar graph. It's actually the reflection image of the original exponential. So to help you visualize that, draw a dotted line diagonally through quadrants 1 and 3. That line is the line y equals x. It is the reflecting line that gets you from an exponential curve to a logarithmic curve. The main focus of the lesson is on the logarithmic curve, the second one that we did, but I wanted students to make the connection to the fact that the logarithmic curve is a reflection image of the exponential curve. They are also inverse images of each other. This equation is an inverse of this equation.